Okay, we're continuing with chapter 1 in the algebra textbook. In this video, we're going to go through the fourth section, which is on quadratic equations. Okay, so as I've been mentioning, the different types of algebraic expressions and equations fall into their own categories. And this can easily seem overwhelming when you think about there's all these different names, and then furthermore, you can have equations in multiple variables, right? But what we've been doing and what we're going to continue to do is I'm trying to show you how this is not nearly as complicated as it seems. So, okay, we talked about what in the pre-algebra chapter, what a polynomial expression is. Okay, but not just in one variable, in any number of variables. So that was like if a polynomial term might be something like, and it's just a term to where each variable is only raised to a whole number power, 0, 1, 2, 3, 4, 5. And this term is polynomial because each variable is only raised to a whole number term. So 0, 1, 2, 3, 4, 5. If you have any negative exponent or a rational exponent or anything else but a whole number, so a positive integer including 0, then in any circumstance in that term or expression, then it's not a polynomial expression. Now here, this term, you say that so like here, 3x squared, this is a degree 2 term here. It has degree 2 because the power is 2. Here, this has degree 2, 3, degree 4. Okay, and so we could do minus 2xy plus 5xz cubed, and this entire expression is a polynomial expression. Specifically, it's a polynomial expression in 3 variables, or a polynomial expression in x, y, and z. Now, it makes sense that the only meaning of a polynomial equation would just be an equation that is made up of entirely of polynomial terms, right? So 3x, y. Okay, here's a polynomial equation in x, y, and z, right? Okay, and so when it came to linear equations, all we were dealing with a linear equation was that the order of any, it was a polynomial equation, a subset of a polynomial equation, to where the order of each term was 1. So that doesn't mean that every single variable is raised just to the first power, because that would suggest that this is a linear term. Well, since the order of this is 2, 1, 2, then this is not linear here. Okay, it's the total order of each term has to be 1. It's polynomial, so it still means that you can't have like this, right, or this. So it's still polynomial, but if the entire order of each term in the entire equation is 1, then it's a linear equation in any number of variables that you want. So 3x minus 2y plus z is equal to 5. The order of each term here is 1 or 0, like this. There's like x to the 0 you can think about. Then this is a linear equation in 3 variables. Okay, now we learned how to solve linear equations in 2 variables specifically in the previous, or in 2 sections ago, okay? So now a quadratic equation, what is a quadratic equation? In any number of variables. In any number of variables, what is a quadratic equation? It's very similar to what we did with linear equations. So meaning it's going to be a polynomial equation, and also you can think about having a quadratic expression as well. Like this is a linear expression. So you could think about, okay, there's also a linear equation. Similarly, here we can think about quadratic equations or quadratic expressions. In any number of variables, it's going to be a subset of polynomial equations or expressions, except to where with linear, the total degree of each term was 1 or 0. With quadratic, the total degree of each term is going to be 2, 1, or 0, where at least one of the terms is 2. Has an order of 2. Otherwise, it would just be linear, right? So at least one of the terms is going to have degree 2, but then the rest can be degree 2 as well, degree 1, or degree 0. But that's the net degree. So in other words, this has the net degree of this is 2. Because remember, with a multivariable term or expression, to get the order of it, you add up the variables of both, or the exponents of both variables. Okay, plus 3x squared plus 2x. It could be, this is linear, that's fine, but since we have at least one of these terms is degree 2, but we don't have anything degree 3 or higher, and it's still, everything's raised to whole numbers, this is going to be quadratic. So 5xz, right? This is degree 2. And so this here would be a quadratic expression in 3 variables, x, y, and z. This here would be a quadratic equation in 3 variables, x, y, and z. Okay? So this can get confusing, but just remember, it's still, linear equations and quadratic equations and expressions are just subsets of polynomial expressions and equations. All right, so, but what we're looking at specifically in this section is quadratic equations in one variable and how to solve them. Now, as I mentioned, when it came to linear equations, you might think, well, man, it's going to get really hard once we have to learn how to solve equations like this, like quadratic equations, etc., in more than one variable. Actually, it works out great. It's not like that at all. Again, it's like, so if we had 3x plus 2yz is equal to 5, well, if we solved for z here, so, okay, 2yz is equal to 5 minus 3x. Divide both sides by 2y, so z is equal to 5 minus 3x divided by 2y. Oh, we just solved a linear equation in 3 variables. You see? So all of the principles that we learn for how to solve these different types of equations in this entire chapter, all these equations in one variable, it's just a simple extension to multiple variables. It's just you have to do it more abstractly with carrying all these variables everywhere. That's it. So, okay. So they give the formal definition of a quadratic equation in one variable, but you can see what it's going to mean. It's any equation that's going to have at least one term where the degree is 2. Otherwise, it would be linear. But then every other term is going to be a polynomial term of degree 2, 1, or 0, which 0 would be a constant. And it's going to be all with one the total number of different variables throughout the entire equation is going to be 1. That's it. Now it says the way it says it more officially here is that let A, B, and C represent real numbers where A is not equal to 0, because otherwise you wouldn't have a degree 2 term. A quadratic equation in the variable x is an equation of this form. That's just a more formal way of stating what I just said. Now, it says A, B, and C are real numbers, okay? However, you can think about how if we could still allow it's similar to with linear equations, we could allow A, B, and C to be any constant. So a constant would be any number in the complex plane. So this would be 2, or you'd have, this is still a constant, right? It makes it kind of seem like I is a variable, but it's not. So you could think about, we're not going to be doing anything like that with these coefficients that are complex coefficients much at all in this entire course. But you can think about the fact that when we get to complex analysis, we could look at, since this is like a constant, we could still have a quadratic equation where A, B, and C could be any number in the entire complex plane. Okay? So, all right. But if we stick with A, B, and C being real numbers, let's say we had 3x squared minus 2x plus 5 is equal to 0. Okay? How would we solve this? What's like a general procedure or procedures that we can use to solve a quadratic equation? Well, it starts off with we're going to see there's 3 different methods we can use. And the first method we use is actually going to be how we're going to think about solving not just a quadratic equation, but really any polynomial equation. And what we do is we can take the any kind of polynomial equation, which is like a quadratic, and we could put everything on one side, all of the terms on one side like this, with the other side being equal to 0, just like this. We can put it into this form. And then from there, what we can do is we can factor the polynomial, like we learn how to factor polynomials in pre-algebra, right? We can factor it into this product of factors. And then with that, we can take advantage of the zero product property, which means that if any one of these factors, so like this is like A, B, C, D, it's this is like these variable expressions, A, B, C, and D. If any one of these factors are equal to 0, then that's going to satisfy the equation. It has to. Any one of these, like you could have A, B equal to 0 and B, C, and D aren't equal to 0. That's going to satisfy the equation. Remember what it means to satisfy an equation. It's when you plug in a value of X into the equation and simplify one side, get a number, simplify the other side, get a number, and those are the same number. Well, if we can, if the A expression equals 0, so like we could take this off to the side. Since whenever we factor a polynomial, we're going to get these simpler factors. This might be a linear factor. So let's say 3x plus 2. Okay, if we plug in x into here and this equals 0, that means that this A expression is going to be equal to 0. That would satisfy the equation regardless of what B, C, and D are, because it doesn't matter what B, C, and D are. You're multiplying them by 0. 0 equals 0. So that makes you, what you do is you set this equal to 0 and solve for x. And that's going to be a solution. Same thing here. Set B equal to 0, solve for x. Set C equal to 0, D equal to 0, and solve for x. Even if they're all equal to 0 at the same time, that's fine. You could take 0 times 0 times 0 times 0. We're not dividing zeros or anything and still get 0. That's fine. And so that's the main way we solve any polynomial equation, using the zero product property. And so like it's not just for quadratic equations, because we can factor any polynomial using the methods we learned in pre-algebra. But once we get to chapter 3, we'll learn more methods using the fundamental theorem of algebra and other properties, to where like you might be thinking, well, okay, from pre-algebra we can't factor any polynomial. There's sometimes we can't factor, we don't know how to factor it. In chapter 3, we'll learn we could take any polynomial and fully factor it, no problem. We're going to learn some more powerful tricks that will allow us to factor any polynomial, all the way down to these linear and quadratic factors. Linear would be 3, like ax plus b. This is linear, but quadratic would be, so we could set all of these different factors equal to 0 and solve. Okay, but you might be thinking, well, okay, but if we had a quadratic factor, how would we solve that? Because like then it must mean that we can't factor this anymore, based on what I just said, right? If using these, what we're going to learn in chapter 3, if we can factor any polynomial, no matter what it is, using those tricks, all the way down to all these linear and quadratic factors. Well, I get how we can set this equal to 0 and solve, right? That's just a linear equation in one variable. But what about this, right? We can't. Obviously we can't factor it, or we would have continued to factor it. So how would we solve this then if we can't use the zero product property? Well, we're going to see as we go through this section. There's 2 other methods we can use to solve quadratic equations, and so in that case we would use one of those methods. So, okay. Let's work some examples. So x squared minus 8x is equal to 0. And now, but before we do this, so we're going to learn 3 different methods to solve quadratic equations. But one of the methods is not going to be, so you might look at this and say, well, we can add 8x to both sides. Okay, now we can divide both sides by x. And what are we left with? X is equal to 8. Okay, and this is not incorrect. This is one of the solutions, but there's actually 2 solutions, and doing it this way, we lose one of the solutions. That's another, because why did that happen? Because the reason why that happened was because we couldn't, remember, when we learned this with rational equations, if we multiply or divide both sides of an equation by a variable expression, then there's an implication when we do that x can't be, or the expression can't be 0. In this case, x can't be 0. And so, but there's, what we talked about when it came to rational expressions, what we talked about was that the way you looked at this was that it's not like you had to note this every single time, at least for non-math majors. We're not going to be vigilant about noting every time we multiply or divide both sides of an equation by an expression that it can't be 0. But the only implication was that when you do that, you need to make sure to go back and check your answer. Okay, and so we can do that here, and this checks out, so we're fine. But here we see there's another implication to look out for. Here, this didn't result in any answer not checking out. Okay, this actually, there's another angle that came into play here. Here we can see that if we multiply or divide both sides of an equation by an expression, the x values that make that expression equal to 0, we also want to plug that value of x into the equation to see maybe if it's a missing solution. With the rational equations, it didn't work out that way because when we did that, we were actually dividing by 0. In the original equation, we were dividing by 0. Okay, but here we can see that 0 was actually a solution that we lost by doing it this way. So if you were going to do it this way, you need to say, okay, I divided by 0, or I divided by x. X can't be 0, so I found that x is equal to 8. Plug that back in. That's a solution. But also, let's plug 0 back in, make sure that's not a solution as well. In this case, it is. But like if we had done that when we solved rational equations, again, that wouldn't have, the restricted x value wouldn't have worked in the original equation. And the original equation, it doesn't matter what this is equal to. The fact that x can't be 0 here, no, all we're trying to do is solve this equation. That's all we're trying to do. This is all that matters. We're trying to find all of the x values that when you plug them in here, the solution, the equation is satisfied. If you plug in x is equal to 0 here, 0 minus 0 is 0, 0 equal to 0, that's a solution. That is a solution. Doesn't matter what the intermediate steps are. If you plug 8 in, that's also a solution. So that's it. Okay? So, but the standard procedure that we're looking at right now is using the zero product property. So we bring everything to one side. It's this polynomial equation, specifically quadratic. So we bring everything to one side. Now we factor. And with the other side equal to 0, now we factor. So we can take out a greatest common factor. And now we're done. That's fully factored. So now we set these factors equal to 0. X is equal to 0. There we go. You see we didn't lose that solution. X minus 8 is equal to 0. X is equal to 8. There's the two solutions. Okay. Let's see. 2x times 2x minus 7 is equal to minus 12. Let's solve this. So, you know, we don't know what we have here. We just have this kind of this jumble of different terms. So let's go ahead and expand everything out and see what we're dealing with. So 4x squared minus 14x is equal to minus 12. Now we can see, look, this is quadratic, right? All the terms are these polynomial terms with total degree 2 or less. So, okay. So we're solving this by bringing everything to one side with the other side equal to 0. Okay, now let's factor the left side. Let's take out a 2 here. So 2x squared minus 7x plus 6 is equal to 0. Okay, so let's see. 6 times 2 is 12. Now you can do minus 4 times minus 3. So we could do, let's see, 2 times 2x squared minus 4x minus 3x plus 6 is equal to 0. Okay, so let's see. We've got, now we can, the grouping is going to work, right? Because we can see, we've got this worked here. 2 times 6 is positive 12, minus 4 times minus 3 is positive 12. So take out a 2x here. You have x minus 2. Now take out a minus 3 here. You've got x minus 2 is equal to 0. So we've got 2 times 2x minus 3 times x minus 2 is equal to 0. So, okay. We have 2x minus 3 is equal to 0. So 2x is equal to 3. So x is equal to 3 halves. You have x minus 2 is equal to 0. X is equal to 2. So that's the two solutions. 3 halves and 2. Okay, now the next method we can use to solve quadratic equations is by using the square root property. And so to show what the square root property, exactly what it is, we start with a simple quadratic equation, and then in the next section we'll see what the more general use of the square root property is as far as solving like any kind of quadratic equation, simple or non-simple. Okay, so what if we had something like x squared is equal to 4? Okay, well that's a quadratic equation. I mean, you can subtract 4 from both sides. It just doesn't have any linear terms. It's a quadratic equation where the coefficient in front of the x squared term is 1, and there's no linear terms. But I mean, we could still have something like, I mean, this would be fine as well. It doesn't matter. But so like, okay, to make this general, let's say we just had this. So x squared is equal to a constant, some real number. K is a real number constant. So how would we? Let's solve this in general. So like we're about to solve a quadratic equation in 2 variables, right? So we could subtract k from both sides. Okay, now we can write this as the principal square root of k squared. This k, we can write the k like this. Okay, now we've got a difference of 2 squares. So we know that we can factor that as okay, so if we set each of these equal to 0, what we get is that x is equal to root k, square root of k, principal square root of k, and x is equal to minus principal square root of k. So we get this. Okay, and so with that, then they give the square root property, which all it says is that if you've got x squared is equal to a constant, then the solutions to that are going to be, so you can, we use the square root property. We typically do this. You take the principal square root of both sides and you put a plus or minus, and you get x is equal to plus or minus principal square root of that constant. That's the square root property. If you have x squared is equal to a constant, the solutions are plus or minus the principal square root of that constant. Okay, now note that we just did this for the case of the principal square root. Okay, this was just for the principal square root. You can't use this property with like any other kind of root, like the 4th root, 6th root, whatever. You can't do that. Okay, now also note that this only allows us to solve this like simplified form of a quadratic equation. So if we had, even if we had like 3x squared is equal to 10, well, we could use the square root property, because we're going to get x squared is equal to 10 thirds. And then so you do and then you would just simplify this radical expression. Okay, but other than this, if we had something like 3x squared minus 5x plus 2 is equal to 0, well, we couldn't use the square root property. We wouldn't know what to do. But we're going to see we can still use the square root property for a general quadratic equation in a second. Okay, now, but also note that we actually can, if we have an equation like x squared is equal to minus 4, we actually can solve this. We can use the square root property, because we know if we have a principal square root of a negative number, we can actually solve that. Only with the principal square roots. This would be plus or minus 2i. Okay? But again, we can't do that if we had like x to the 4th is equal to minus 16. Well, we couldn't even use this. We wouldn't have a property we could use. Like, there's no property. We'd have to do it. The only way we could solve this up to this, with what we learned up to this point, is to just put everything on one side and factor it. We don't have this property we just developed is the square root property. And then furthermore, even if we did develop a property that involved a radical with a 4th root or something, we couldn't solve this, because we can't simplify a radical with a negative underneath unless it's an even root radical with a negative underneath, unless it's the root is 2. Okay, so, all right, let's solve these equations here. If we have x squared is equal to 64, okay, well, square root property. What's the principal square root of 64? That's 8. There we go. There's two solutions. And that makes sense because there's two numbers that when you square them, you get positive 64. Positive 8 and negative 8. Okay, 2y squared plus 36 is equal to 0. So you have 2y squared is equal to negative 36. Divide both sides by 2. You have y squared is equal to minus 18. So y is going to be equal to plus or minus the principal square root of minus 18. 9 times 2 is 18. So we could take out a 3 and let's take out the I, 3i, plus or minus 3i root 2. Okay. Now let's see. Last example is w plus 3 squared is equal to 8. Yeah, we can still apply the square root property here because it's like you can think about, well, if you set x equal to w plus 3, then what do you have? X squared is equal to 8. That's the exact form we use for the square root property. So it's the same idea. It's just, you could just take the square root, the principal square root of both sides. And when you do that, you put that plus or minus. So you're left with w plus 3 is equal to, okay, this is 4 times 2. So we've got 2 root 2 plus or minus 2 root 2. So we've got w is equal to plus or minus 2 root 2 minus 3. You see, so one solution is 2 root 2 minus 3. Another solution is minus 2 root 2 minus 3. Okay? Now, with that then, we're going to move on to the idea of completing the square because remember, there's 3 different methods we use to solve any, we're learning in this section here to solve any different, to solve any kind of quadratic equation, no matter, in general, no matter how complicated or simple or whatever, right? The first method was the zero product property method, the factoring everything on one side. Now we're going to use the square root property. However, as you can see, we can only solve these kind of simpler quadratic equations that they don't have any linear component. So how can we use the square root property to solve any quadratic equation? So that's what we need to first learn about completing the square. So, okay. It says in example 2c, the left side of the equation is the square of a binomial and the right side is a constant. Right? So it's saying we had this binomial here, the square of a binomial, with the right side being a constant. That's what the last example we just did. Well, with completing the square, we can take any quadratic equation and, like if it's got, so ax squared plus bx plus c is equal to 0, where a is not 0, b is not 0, c is not 0. It's as complicated as it gets, and we can use completing the square to put that into a form just like this. Just like this, where we can solve that. At that point, we can solve that using the square root property. Okay, so how do we do this? Well, okay, first let's do a reminder here of the perfect square trinomial, right? This was just if you had a plus b. We learned this in pre-algebra. A plus b squared. And it was a trinomial in the sense that if a and b were these polynomial terms. But you could apply this with anything. But thinking about polynomials, what we got was a squared plus 2ab plus b squared. Okay, and so they show some examples here, but in the case of like x plus 5 squared or t minus 3 squared or p minus 7 squared, like you could have a plus b or a minus b. And here's so a minus b squared was a squared minus 2ab plus b squared. Right? They show some different expanded forms of these different binomials squared. Okay, so what are we going to do with this? Well, okay, here's the idea. What we want to do is, this is the process of completing the square. What we're going to do is, so if we had 3x squared minus 5x plus 11 is equal to 0. We want to solve this. Well, what we can do is we can kind of focus on this pair of terms here, okay? And we can think about adding an additional term on the back end of this pair of terms to where we create a perfect square trinomial, right? We can like manufacture this. So if a perfect square trinomial, if you have x plus some constant, plus or minus some constant, I'll do that, plus or minus some constant squared is equal to x squared, then plus or minus 2ax plus a squared, right? Well, we've got these first two terms here of a perfect square trinomial, 3x squared. Well, yeah, it's kind of hard to see. In this case, we would have, we'd have to get the coefficient of 1 in front of the x. So we do that first. We would do that first. So we would take this and divide the entire equation by 3. So you'd get x squared minus 5/3 x plus 11/3 is equal to 0. But it's nice if you actually already have a coefficient of 1 in front of the x squared, that's fine. Now we focus on these two terms, okay? So again, if you square a binomial, x plus or minus a constant, a binomial like this, you get x squared plus or minus 2ab plus a squared, right? So we can see that we've got the first term, x squared here, and then this is like the 2a, this is 2ax, not 2ab, 2ax. Okay, this corresponds to the 2ax term, right? And so if all we need to do is figure out from these two terms what a is, and then take a squared and add it here. And then we'll have created this perfect square trinomial. Now you might say, well, no, we can't just add something to an equation like that. You're right. So what we do is we also add it to the other side of the equation. That same a squared. A squared is going to be a constant. And so then what we're going to be left with is, so watch, let's do this. So, okay. In this case, we can see what we've got is so we can actually make this more general. If you just do, and for the completing the square, if you just put a plus here, if you just write this out as plus, then that'll make it easier for all cases, because now we can see that, so 2a, we can match this up and see that 2a is equal to minus 5/3. Right? If we're matching this up. So we divide both sides by 2. We've got a is minus 5/6. We square that. What do we get? 25 over 36. So let's add 25 over 36 to this expression here, but also, so we don't change the equation, add it over here. Okay? And so what does that mean? What have we done? Well, okay, we can erase all this, but just keep in mind what a is. A was minus 5/6. So let's not forget, I'm going to rewrite a. A is minus 5/6. Okay. So if we focus on this trio here, this 3-term expression, well, we just created a perfect square trinomial. Right? So we know we could just go ahead and rewrite this as x and then do, right? We can rewrite it like that. But now what's left though? What's left? Okay. Now over here, okay, now we're in business because we can do x, we can subtract 11/3 from both sides. So, okay, 11/3 is 12 times 3 is 36. So what's 12 times 11? 2, 1, 0, 2, 1, 132. So, okay. 25 over 36 minus 132 over 36. And what we're going to get is a, so let's see, minus 107 over 36. We get a negative number, but you see, we end up with this binomial squared and a constant on the other side. We can apply the square root property now. Here we're actually going to have an imaginary number, but that's the idea. Okay, so here they just give an example of completing the square and then outline the process for solving a quadratic this way, but I think I just outlined it pretty well for you. But let's work a couple of examples so you can see this clearly. Okay, so let's see. X squared minus 3 is equal to minus 10x. Let's solve this quadratic equation. So, okay. We have x squared plus 10x minus 3 is equal to 0. Now we want to create a perfect square trinomial out of these two terms here. So we can just use, so x plus a squared is equal to x squared plus 2ax plus a squared. We can see in this case 2a is going to be equal to 10. Right? Here's the x squared. Here's the 2ax term. So a is equal to 5. Okay, so with that, a squared is 25. So we can do this. We can add 25 here and then add 25 here. And so what we get is this x squared plus 10x plus 25 is x plus 5 squared. And then we're left with minus 3 is equal to 25. So x plus 5 squared is equal to 28. Okay, so now we can apply the square root property, and we get x plus 5 is equal to, so 7 times 4 is 28, so we can take out a 2 here. Okay, now we can subtract 5 from both sides, and there we go. Okay, now this next example is, yeah, so we have this leading coefficient that's not equal to 1, so we just divide by that leading coefficient, and we get x squared, and then plus 3/2 x plus 5/2 is equal to 0. Okay, but then you just go through the whole process again. So here we can see that 2a is going to be equal to 3/2. So a is equal to 3/4. A squared, therefore, is equal to 9/16. So we add 9/16 here, and then also add 9/16 over here. And so we're going to get x plus 3/4 squared plus, okay, and so we're left with, let's see, plus 5/2 is equal to 9/16. So we've got 9/16 minus, and then, okay, 5/2 is, so 8 times 5 is 40. So this is negative 31 over 16. So x plus 3/4 squared is negative 31 over 16. So now let's apply the square root property. So x plus 3/4 is equal to, let's see, we can take out an I, and we're going to get what? So x is equal to minus 3/4 plus or minus root 31 over 4i. And there we go. Okay, in the next video, we'll finish off this section.